Welcome to Thermochemistry Day 2. Today we're going to be interpreting heating curves and phase diagrams. To begin with, we're going to look at matter and change. You've been seeing these state particle diagrams for a long time now, I'm sure, probably since about 4th or 5th grade. There are three basic states of matter. Solids have a definite shape and volume. So right over here, that's going to be a solid. They're very tightly packed together. Liquids, right here, can change their shape, but they still have a definite volume. The best example I can think of is if you go to the grocery store and you see containers of milk. Sometimes you'll see them in the rectangular prism kind of containers, and then other times they'll be in the more cylindrical. They're both still half a gallon, but they can change shape according to their container. And then finally we have gas. These can change shape and volume to match their containers, and if you can see, if you look really closely, you can see the little lines coming off the gas molecules, and that is representing motion. So they're moving really fast. Alright, so when we're talking about our state changes, matter can change from one state to another, and there are 6 possible state changes. For each, energy is either absorbed or released. This last one you see is plasma. We're not going to talk about that very much in here, but it is just something that you should be aware of. Here are our state changes. The first one is freezing. That's when a liquid goes to solid. The next one is a little more unusual. It's called sublimate. That's when you go from a solid to a gas. This happens with dry ice, for example. The reason it's called dry ice is because it does not melt, it sublimates. So it goes directly from solid dry ice into a gas state. Next we have condensation. That is when a gas goes to a liquid. Good example of that is soda. On a hot day, we'll get those condensation beads on the outside, or in the morning when grass is wet and dewy. All right, our next state change is melting. That is when you go from a solid to a liquid. Then we have evaporation, when liquids go to gas, like if we're boiling water. And the last one is called deposition, and that's when we go from a gas to a solid. One common example of this is snow, something we all saw not too long ago here in Texas, which was very unusual for here, but that is when you have, like for example, a cloud, and it comes down as solid snow, skipping the liquid state. Okay, so here is just a diagram of all of these state changes that we just talked about, and this can be very helpful for you to kind of picture what's going on here. Again, sublimation and deposition are usually less familiar to most students, but there they are. So when we're talking about state changes, one important new vocabulary word that we're going to introduce is the word entropy. Entropy is just the measure of randomness and disorder in the universe. So the universe is always trending towards randomness and disorder. And the more and more closely we get to the gas state, the more and more the entropy is increasing. So solids, as you can tell from this particle diagram, do not have a lot of randomness in them. They're tightly packed together in a pattern. Liquids, a little more randomness, a little more entropy, and then our gases are quite randomly placed. So, as we move from solid to liquid to gas, we increase entropy. So processes that increase entropy are things that are going to get you closer and closer to a gas state. Things that decrease entropy are getting you closer to the solid state. So the universe consists of matter and energy. Energy does not have mass or take up space, but energy is involved when matter changes from one state or one phase to another. For example, let's think about something like ice, which is a solid. If we add some heat energy to that, it will turn into a liquid or water, and it has gone through the state change of melting. So we can do a thought experiment where we say, what happens to the temperature of a block of ice when you put a Bunsen burner underneath it? Most students would think that the temperature goes up smoothly, but that is actually not what happens. There is a graph of temperature versus time, and this is what we call the heating curve. Right now we're going to look at the heating curve for water. Okay, so if we're considering this heating curve for water, here's what we're going to see. So imagine again we have a block of ice that is being slowly heated by a Bunsen burner. So ice at negative 30 degrees Celsius absorbs heat, and this will slowly cause our temperature to rise to 0. So this is what we first see. Once that ice is at 0 degrees Celsius, it will absorb heat and melt at a constant of 0 degrees in order to reach the water state. So as you can see here, our curve suddenly becomes flat. It's going to stay flat. When all the ice melts, water at 0 degrees Celsius will absorb heat and the temperature will rise again. So once all that ice is melted, we will see that rise in temperature once again. So we've had a rise, the flat space, and then another rise. Once all that water has absorbed heat and begins to boil, it will once again hit another flat area while it is going to boil at a constant temperature of 100 degrees Celsius. Finally, temperature of the steam will rise once again. We're going to see a rise in temperature as it absorbs heat after all of the water boils. So go ahead and label your notes with all the phase changes. Let's think about this. What is our phase change happening? And I am going to show you these labeled with our phase changes. Okay, so our first phase change when we're going from ice to water is freezing, going in one direction. So from ice or from water to ice, we have freezing. But if you're going from ice to water, there's melting. And what you're left with is water and ice. Okay, so moving from water to ice, from right to left, you have freezing. Moving from left to right, you have melting. All right, our next phase change, once we move from water, when we heat up water, we see boiling to create gas. If we go the opposite direction, from gas to water, we have condensing. But these are all occurring at the same temperature. It just depends if we're adding heat or removing heat. So boiling and condensing will happen at the same step. Freezing and melting will happen at the same step. So what we wanted you to notice is that freezing point and melting point are equal, and boiling point and condensing points are also equal. And this is just another picture of that. You might be wondering, why is this curve flat at some points? Well, during phase changes, temperature is staying constant. So between B and C and B, and also D and E to D, the temperature is not changing. That is because at that time, the solid, in the case of B and C, is becoming liquid, or the liquid is becoming solid. Now we're going to move to do a sample problem. It says, between which 2 points is the water boiling? We're going to switch it over to document camera. Okay, between which 2 points is water boiling? Okay, so here we've got ice. I always like to label these, like if you're on your test, I would always label your different points. We've got ice, we've got water, and we have gas. So water will boil between points D and E, because that water will change to gas between points D and E. Okay, number 2 says, what is the phase change as you move right from point B to point C? So as we move to the right from B to C, so we move to the right, we're looking for that phase change. So our phase change between ice to water. What happens to turn ice into water? That is melting. Now notice if it had said moving to the left, then we would have said freezing. Okay, but it said right. Number 3 says, what is the phase change as you move left from point E? So we're moving to the left to point D. So we're going from gas to water. We're trying to think of that name. That is condensing. What is happening to the temperature between points D and E? Now here's the part where it comes in handy to know how to read a graph. Okay, temperature is on the y-axis. So between D and E, we can look at our graph. What is happening to the temperature? Absolutely nothing. It's flat. There is no change in temperature during phase changes. So while that water is becoming gas, the temperature is constant. There is no change. And this is really important. I want y'all to take note of that. During phase changes, there is no change in temperature. That's why the graph is flat. All right, number 5 says, what is happening to temperature and energy as you move from point D to point E? Okay, so this is very similar to 4. So temperature is staying the same. We already figured that out. So we're going to cross these other ones that are saying that it'll change. I'm going to eliminate those as choices. And then once again, we're moving from D to E. So from D to E, from water, and we're going to gas. So it's not melting because that's way down here. So I can eliminate choice C. So it's going to be choice D. Temperature stays the same as it boils. Okay, very good. The next type of diagram we're going to look at is called a phase diagram. And what a phase diagram will do is summarize the effect of temperature and pressure on a substance in a closed container. Please note, on your test, these will not be labeled for you. But remember, you get open note tests, so if you take good notes on what these areas are, you'll get all these questions right. These diagrams are always divided into 3 areas, which represent the solid, liquid, and gaseous state of the substance. These will not always be labeled for you, so you really want to make sure you've got them labeled: solid, liquid, gas. One good way to remember these is to know that solids are more common at low temperatures. So over here, since your temperatures are on the x-axis, there's a low temperature. And gases are more common at high temperatures. So if we go to the end of the x-axis, that's where your gases will be. The liquids are just kind of right in between. So that can help you remember where these are. Point A, that's circled on here, is called the triple point. What the triple point is a representation of the only point in the phase diagram where all 3 states can coexist. So at this very specific temperature and pressure, this substance can exist as a solid, liquid, and gas. So, for example, this diagram shows that the triple point of water is right here. So at 0.1 degrees Celsius and a pressure of 0.006 atm, ice, water, and steam can all coexist. This is a very narrow, specific point. So it's pretty rare conditions. Now let's do some sample problems. One thing you want to keep in mind when we're looking at these sample problems is that we want to first label our states. So this is going to sound kind of funny, but I'm going to tell you this is a good way to remember this. It is kind of funny. These tend to kind of look like, for not to be crass, but it kind of looks like a behind, right? So you can see that this would be our triple point where all 3 come together. And this is going to be the gas. This is going to be a liquid. And this is going to be a solid. So some people always sometimes refer to these as butt diagrams. That's kind of what they look like, but if you don't like that, you don't have to think about that. But it does help you remember at least probably gas. What is the temperature of the triple point on this diagram? So here's our triple point. So, and we're just looking for temperature, so be careful not to mix up your X and Y axis. It's not asking me for the pressure, it's asking me for the temperature. So the temperature is -15 degrees. Okay, the next one says, if a sample of this substance is at 50 degrees Celsius and a pressure of 6 atm, what phase is it in? So this is just very basic graphing. Okay, so we're at 50 degrees Celsius, so right here. And we're at pressure of 6. So 6, this is my pressure, and it's just draw your little lines. That's in gas. Simple as that. Next one says, if a sample of this substance is at 0 degrees Celsius, so if we're at 0 degrees Celsius, that's right here, and a pressure of 30, This one is very borderline. As we can see, this one's pretty close. So sometimes it helps to have a straight edge, right? So you just want to be sure if you're not good at drawing straight lines like me. So now I can get another piece of paper so I can really make sure that my line is good. Especially when it's close like that, it's handy just to get a straight edge to make sure. So once I made my straighter lines, initially I was thinking solid, but after I straightened out my lines, you can see that it falls there in the liquid phase. So use that extra paper or a ruler sometimes to make sure your lines are precise. Okay, so if a substance moved from region B to C, from B to C, what phase change is occurring? So this is asking us to think about what happens when you go from a liquid, and think about water if it helps you. What happens when water goes from a liquid to a solid? It becomes ice. It does that by going through the process of freezing. Great job on that video. Remember, use a straight edge or a ruler if you need to, another piece of paper to make sure your lines are straight, and just make sure you take note of where those areas are.